talk a little distance formula. So certainly if you can look at this examples and just kind of know what's going on, that's cool. If not, here's this video so you can again play it back over and over again. This way you can have those examples at the ready to help you navigate the distance formula. So just like the Pythagorean theorem notes, I think I'm going to do these first two as one video, and I'll do the second two as a separate video. And so there'll only be two covering all these problems. So let's just jump into it. All right, so this first one is actually right off the front note sheet. If you notice, we didn't actually find the distance. We were talking more about how the distance formula bases the Pythagorean theorem. And so here's where we can actually carry this through. And so just like with the Pythagorean theorem, you have to make sure that the distance formula applies and you have the right stuff to operate it. In this case, the stuff you need to operate it is actually going to be these points. More to the fact that you need coordinates for these points. Now, I think they were labeled on the previous side, but this should be something we can easily do. So the coordinates of P1 looks like we're going to have 2, 8. Okay, and then we'll drop down here. Let me switch colors for P2, point number 2. We're going to have 7, 3. Okay. Now we could go the Pythagorean theorem route, and I want to validate that. So in other words, just like the previous example, like if you want to, we can draw. If you wanted to, you could totally draw on a triangle, find the side lengths, and just calculate using the Pythagorean theorem. But the distance formula actually gets around that. You don't actually have to use the Pythagorean theorem to solve this, as long as you have points. And so if you kind of understand like the Pythagorean theorem being c squared is equal to a squared plus b squared, I just flip the formula around. And because an equation you can flip sides and it doesn't really matter. And there's a reason why I look at it, and this might make a little sense. So if you look at the Pythagorean theorem as c squared equals a squared plus b squared, and you want to get rid of the square, of course you square root it. And so if you think about the resulting Pythagorean theorem, well, that would just give you a c because those would cancel. And this would be the square root of a squared plus b squared. Now, the reason why I'm bringing that up now before we start to talk about distance formula is because I want to make sure you guys have a clear sense, or at least give you an opportunity to have a clear sense to see where the distance formula is coming from. And so if you're calling the Pythagorean theorem, a and b are just side lengths. Well, if you look at the distance formula, we have d for distance, square root of x2 minus x1 squared, and then we have y2 minus y1 squared. And so if you look, we have like this a, which is a side length, and then we have this x2 minus x1 business, which again, if you think about the previous notes, like that's literally just a calculation for how long a length is in the x direction. Same thing with the b, that's replaced with y2 minus y1, and that's just going to tell you like a vertical change of your equation. And so when I was saying that the distance formula and the Pythagorean theorem are very similar, this is what I'm talking about. Like if you look, they're almost the exact same formula. I mean, they are exact same formula in a very, very similar form. If you notice here, we have a big square root of everything. We have a being solved out using points, and b being solved out using points, because that's how the distance formula takes information. It lives exclusively on the grid, and so it needs points to operate. Okay. With that being said, let's go ahead and just kind of get this into the formula. So we're going to focus in on the distance formula, this guy right here. Okay. And so we just have to replace it with the parts that we have in our grid above. So I'm going to do a little rewrite in the formula here. So we have d is equal to the square root of x2 minus x1. Well, those just come from the points. x2 and x1 just refer to the different points we have here. So this guy right here, 7, is the same thing as x2. This guy here, 3, is the same thing as y2. And I'm getting those 2's because this is a second point. It's labeled as p2. Okay. This 2 right here is the same thing as x1. Let's go green. And then this 8 is the same thing as y1. And so it's just a matter of pulling these points in as we're writing. Okay. So let's go ahead and do that. Let me set up the structure first here. So we have something in parentheses being subtracted squared, plus another thing in parentheses being subtracted squared. Okay. And so we need x2 and we need x1. So again, looking up here, x2 is just going to be the 7 value. X1, which I'm grabbing from the other point up here, is going to be a 2, so I'll stick that right there. And now I just continue. I need the y2 point. Well, y2 is going to be this 3. And then I'll subtract off the y1 point, which is going to be this 8 up here. All right, so the distance formula is considerably more messy than the Pythagorean theorem at first until you get the hang of it. And so it's a lot more places certainly that we can kind of miss arithmetic. So anyway, let's continue solving, excuse me. So we have 7 minus 2, which is 5. Okay, we'll leave in parentheses with a square. And then 3 minus 8 is going to be negative 5, which we'll throw in with a square there as well. Now we're just going to continue our arithmetic. And so you might look at this negative 5 and think, well, can we have a negative if we're talking distance? Well, no, we can't, but in the end, I don't think it's going to be a problem, and you'll see here in the next step why. So we have 5 squared, which is 25. Plus we have negative 5 squared. Well, negative 5 squared just means negative 5 times negative 5. Well, negative 5 times negative 5 is going to be 25. Two negatives make a positive, so this is going to be 25 as well. Okay. Make a little more room here. There it goes. Okay. So we're not quite done here. We have to keep solving. But we have the square root of 25 plus 25, which is the same as the square root of 50. This in itself is actually a really good answer, and you can actually leave your answer just like this. If you want to take it to a calculator, we can do that as well. And so we have 50 square root, and again, we have to do some rounding here, and so the distance is going to be approximately equal to 7.071. Okay. And so although this is a messier process than the Pythagorean theorem, it nevertheless does find a correct answer. The thing to note here, if you want to connect this to the Pythagorean theorem, is this step right here. We have this guy right here, this step, where we have 5 squared and 5 squared. Well, if they come from A and B, and we look back at our example, what they're really saying is that these two distances here are both 5. And if you look, they actually are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, I know one's negative, but that just has to do with like direction of counting. The important thing to note is that they're both 5, right? And so in this case, we're going to we see it mimics the Pythagorean theorem almost exactly. And so we're going to have just 5 squared and 5 squared, right? And so this is a trustable way to find a distance, to find a length. You could, again, always revert back to, say, like drawing the triangles using Pythagorean theorem. But distance formula works just as well here. In some instances, it actually works a whole lot better. Okay? So I'm going to stop this video here because it's actually running long, and I'll get the second video, second problem in the next video. All right, thank you.